Hi guys, this is Miss Kabani again from Saxe High School. Mr. Askins and Mrs. Sawyer will also be using this video. Right now I'm on page 9 of your gases packet, and we want you guys to do 1 through 4 for practice and then upload those to Google Classroom. Okay, so you guys are going to try out 1 through 4 on your own. Here, you're going to use Avogadro's principle to get from moles to liters. Here, you guys are going to use the ideal gas law, or you could also use Avogadro's principle as well, because 0 degrees Celsius and 1 atmosphere is standard temperature and pressure. So because these are at STP, you can use Avogadro's law there. Okay, same thing with number 3 and number 4 as well. Okay, so use those to solve for the first 4 on page 9. Okay, and now what I want to get to is something called gas to gas. So with gas to gas, we can use the coefficients in the balanced reaction to represent the number of moles of each substance, which can't be measured, but can easily be converted to using molar mass. When a reaction is done between 2 gases, the amount of each gas will generally be measured in liters instead of grams. This makes it difficult to do calculations unless gases are at standard temperature and pressure. So basically what we're saying is we can use a balanced chemical reaction, and based on that mole ratio, we can convert from liters of one gas to the liters of another gas. Okay, so here, if you have a given volume, okay, and then you convert from that volume to moles, you're dividing by 22.4 liters. Okay, then you use the mole ratio to switch over to the next step, and then again you end up with liters over moles. Okay, so this is actually very redundant because this and this are going to cancel out. Okay, 22.4 divided by 22.4 is 1. So this is going to get canceled out and this is going to get canceled out. Okay, so actually an example I'd like to give is, say for example you have the synthesis of ammonia, which is nitrogen gas plus hydrogen gas makes NH3, that's ammonia. Okay, to balance this, remember everything has to be balanced. We need 2 ammonias, 3 hydrogens, and 1 nitrogen. Okay, so for example, if I wanted to go from, let's say I had 5 liters of nitrogen. Okay, so if I have 5 liters of nitrogen, okay, to go from liters to moles, I'd have to divide by 22.4 liters for 1 mole of nitrogen. Okay, and if I wanted to see how much ammonia that would make, I would need my mole ratio. So that's 1 mole of N2 for every 2 moles of ammonia. And then to go from moles of ammonia to liters, again, I'd have to use the 1 mole of any gas can occupy 22.4 liters. Okay, so if you notice, this is, again, very redundant. The 22.4 and the 22.4, these are going to cancel out. Okay, so instead of us going through all of this and doing the 22.4 liters, if you have a balanced chemical equation, all you really need to do to convert from liters of one substance to the liters of another substance is simply to look at the mole ratio. Okay, so it says in this case though, because the molar volume of every gas is 22.4 liters, it will cancel out and simplify the stoichiometry as long as you use the coefficient from the balanced chemical reaction as liters instead of moles, okay? Basically, we're going to be using the mole ratio, and that's going to tell us how many liters there are based on that equation, okay? This only works with gases when you're given and the unknown are both liters. So basically, we're going to go from liters of one gas, of gas A, to liters of gas B. Okay, so this is going to make a little bit more sense once we do a few examples, okay? Basically, what we're saying is if you have a chemical reaction and you know that mole ratio once you balance it, if you want to go from liters of one substance to the liters of another substance, you can use the mole ratio if it's at standard temperature and pressure, because the 22.4 liters is going to cancel out here and here. Okay, so we're going to try to avoid this redundancy here. Okay? So on the top of page 10, okay, we have, this is kind of what I was just going over. It says calculate the volume in liters of ammonia. So my unknown is liters of ammonia, and I'm given 5.5 liters of hydrogen gas at STP. So because this is at STP, I'm allowed to use Avogadro's principle that 1 mole of any gas will occupy 22.4 liters, okay? But again, since I'm going from volume of one substance and I'm given the volume of another, this is called a gas-to-gas problem. And with gas-to-gas problems, all you need to do is look at that mole ratio. Okay, so here I'm given 5.5 liters of hydrogen. Okay, I'm going to set up my train track. So since I have hydrogen up here, I'm going to cancel out using hydrogen down here. And my unknown is ammonia. So ammonia is going to go up here. Okay, so we got to look at the mole ratio. There are 3 hydrogens for every 2 ammonias. So that mole ratio is what I'm going to use to convert from hydrogen to ammonia. Okay, so basically this is going to say 3 liters of hydrogen make 2 liters of ammonia. Okay, so I'm allowed to say that these are the number of liters because, like we proved in the other page, it will cancel out with the 22.4 liters. Okay, so we would just do 5.5 times 2 divided by 3, okay, and that will be 3.6 liters of ammonia. Okay, so this cancels out, I'm left with liters of ammonia. Okay, same thing for the next one. It says calculate the moles of water vapor, produce with 10 liters of oxygen reacts with excess hydrogen at STP. Okay, so again, because it's at STP, I can use the Avogadro's principle. Okay, so I have my given is 10 liters of oxygen. That's my given. All right, what I'm trying to get to is the moles of water vapor. Okay, so since I'm at STP, I know that 22.4 liters of oxygen will occupy 1 mole of gas. Okay, now since I'm trying to get to water, I need the mole ratio step here because we are switching over from moles of oxygen to moles of water. Okay, so remember with stoichiometry, every time you wanted to go from moles of one thing to moles of another, you need the mole ratio. So I'm going to set up one more train track. Okay, and I'm going to look at my mole ratio. Per the equation, 1 mole of oxygen will form 2 moles of water. Okay, so you can see here my moles of oxygen have canceled out, and my liters of oxygen have canceled out, and I'm left with moles of water, which is what I want. So you're going to do 10 times 1 times 2 divided by 22.4, and that will give you 0.893 moles of water. Okay, for the last one, we are given 15.5 moles of methane. We're trying to find the liters of carbon dioxide, okay? So again, like always, you want to start with your given. I have 15.5 moles of methane. Set up your train tracks. Since I'm in moles of methane and I want to get to moles of CO2, I'm going to have to use my mole ratio, which coincidentally is 1 to 1. So I have 1 mole of methane goes on the bottom because I'm trying to cancel out methane for every 1 mole of carbon dioxide. Okay, and now at this point I've canceled out moles of methane and I'm left with moles of carbon dioxide. But remember, they want liters. So if I want to get to liters, and since this is at STP, I'm going to use Avogadro's principle, which says that 1 mole of any gas will occupy 22.4 liters. Okay, so this is going to get me liters of carbon dioxide. So my moles are going to cancel and I'm left with liters. All right, so essentially you would do 15.5 times 22.4 because everything else is 1. Okay, and you would get 347.2 liters of carbon dioxide. Okay, so I want you guys to practice the bottom of page 10 on your own, and you will upload that as well. Okay, thanks.